Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Galileo is famous in this story because he was the first person to seriously augment his senses in his study of the universe, of looking at the sky. In 1609, Galileo heard rumors of a device that would magnify your view of a distant object, something called a telescope. He promptly, just from the descriptions that he'd heard, put together a device that would magnify things by about 3 times. And then, being a very clever person, he sat down and thought about it and made one that would magnify things 30 times, a much better kind of device. Let me give you some kind of a sense of how it is that a telescope works, just a very basic sense. A telescope consists, first of all, of an objective, a main focusing element. And that objective might be something like this lens that we have right here. So this lens that we have right here, it's just a little glass lens. I'll hold it up so that you can see what it looks like, a glass lens. That lens is capable of producing an image of an object. So here I have an object. It's a bulb that has a bunch of filaments that run in parallel with one another. Those filaments, if you were to look at them unimpeded, are very bright. You can see that from the light that's coming off here. You could look directly at this object, see the light emitted from it, and tell what the object is about. What a lens like this does is it forms an image of an object. And that image is a place in space from which light comes as if it was coming from the object. So when we look over here on the wall, what we see is an image of those filaments. And when we look at that, we're seeing something from which light comes as if it was the object itself. It's a copy of the light coming from the object. That's what an objective does, is it forms an image of something else. So there's another place now from which light comes as if it was really the object. All right, that's basically what an objective does. And what Galileo did was to take a lens like that, an objective lens, and use it to form an image of what was out there on the sky. So instead of looking at the sky to see the stars, you could look at this place right here to see the stars. Instead of looking at the filament, you could look at the wall over there to see an image of it. So that's what the objective of the telescope does. It forms a copy of the object itself, and that copy is a place from which light comes as if it was really there, as if it was really in that spot. All right? What's the other part of the telescope? Because most of us know that Galileo's telescope had 2 pieces. It had an objective and an eyepiece. Well, the purpose of this eyepiece in Galileo's telescope is really just to magnify the image. There is this place right here from which light comes as if it was really where the object is. And Galileo could have taken a piece of paper and stuck it there, and then just like we can look at the wall there, he would see the image of the sky projected right there on that spot. But he wanted to magnify it, right? So he used something that is effectively a magnifying glass, right? He got another lens and went and looked at that image. So although they're lined up like this, that's really what's going on in this simple telescope. You have something that forms an image, and then you look at that image. Or later on in our story, you'll see instead of putting an eyepiece on and looking at the image, you can just put a piece of film here and take a picture of it, or a digital detector, as we'll do later on. Okay, so that's the basic idea of how Galileo's telescope worked. Let me give you a sense of how well it worked, because it's kind of hard to recall this. This is a picture taken in Paris, looking out over a telescope that is meant to function just about like Galileo's telescope did. So you see here the rooftops of Paris. This is actually looking out of a United Nations building in Paris. And this little telescope. So if you didn't have Galileo's telescope, that's what you would see. You would look out. You could see a lot, right? There's a lot of details there. But if you could magnify things, you could see more. And Galileo's first step was to look through something that magnified things by about a factor of 3. And if you did that, then you would see that this part of the scene out here would get, bigger, and you would be able to see more details. So this was the first step that he took. But then he improved things so that he would be able to magnify things by about a factor of 30. And when he did that, when you look through this little telescope, which is like Galileo's telescope, you suddenly see a lot of details, like a big construction crane with its control tower and everything else, that you wouldn't have seen there at all. And this gives a sense of what happened when Galileo looked through the telescope pointed at the sky. He was able, for the first time, to see a bunch of things that people simply couldn't see before. Augmenting his vision was the crucial step that he took. That's not the only thing that Galileo did, though. His contribution here really is twofold. First of all, he thought to turn a telescope to the sky, while most of the people who were using telescopes were watching out for their competitors' ships. Right? So he thought to use this for another purpose. That was important. He showed that instruments with magnification like a telescope can allow us to learn more about what's really out there by augmenting our senses. So instead of just using our senses and trusting only our senses, he got us to use instruments to do that. The second thing he did was to observe really carefully and to record what it was that he saw when he observed carefully. He thought about what it meant very carefully, and most important, he published what he found. Science exists only because we share what it is that we learn. Without this, every one of us would need to encounter the world completely afresh, learning everything from our own experience. And there's none of us, not Newton or Einstein or Feynman or anyone else, who could figure out on their own what we have done collectively through science. And this fact of publication, which is shown here, this is a copy of the book in which he published this, or the front page of that book. Without this publication, everyone would have to rediscover everything that he discovered. And because Galileo was also at the beginning of this period of sharing what you discovered instead of keeping it secret, that's one of the main reasons that he's considered one of the founders of science. Galileo did this publishing in this little book called Sidereus Nuncius. It was written in Latin. His later books would be written in Italian to make sure that everyone could understand them. Right? When he wrote in Latin, it was for a very narrow audience. But he was still writing in Latin at the time. And in this book, Sidereus Nuncius, which was published in 1610, very shortly after he made these observations. I note this because I looked at this yesterday, and there's the date in Roman numerals, and it just looks so different from the dates in Roman numerals today. It was really a little unnerving to me. It's an old book. So he discovered three big things in this book. He reported three big things. The first one is that when he looked at the Milky Way, instead of being milky and just some kind of smooth fluid, he found out it was actually made of millions of stars. Immediately changing our picture of what the sky was like. This Milky Way was not made of something smooth, but of millions and millions of stars. A second thing that he observed was that when he turned his telescope to the moon, not only could he see a lot of details on the moon, but he carefully interpreted those details to tell him that the moon has a landscape. The moon is not a perfect object at all. It has mountains and valleys, things very like what you might see on the Earth. All right? And that required careful argument and interpretation. So this kind of picture is meant to show the arguments that he made. Look, you can see how there are shadows on the moon. There must be mountains and valleys. So thinking about what he saw was also an important part of this. The third and perhaps most famous thing that he saw was that the planet Jupiter was accompanied by a set of 4 little planets, he called them, that orbited around Jupiter. He was a smart man, so he quickly named these the Medicean planets. Right, and told the Medici that he had given them 4 planets, which they did appreciate. Later on, he would add to these astronomical discoveries, later on meaning in the next year or two, he would add to these astronomical discoveries 2 more really important ones. One is that he saw that Venus shows phases like the moon does when it orbits the sun. And you can see here his drawing of the phases of Venus, which show not only that the phases change, but that the apparent size of Venus changes in concert with those changes of phase. And finally, the last big thing that he did in astronomy was to show that not only is the moon imperfect and have a landscape and so on, the sun, the very sun, is also imperfect and shows spots like this. All right? So these are sunspots that he drew in May of 1612. Now, the reason that these discoveries were important is kind of twofold. There are 2 principal reasons why Galileo's observations are astrophysically important. The first is that the discovery of that other little solar system around Jupiter and also of the phases of Venus provided very strong evidence for the Copernican picture of the solar system in which the planets orbit the sun rather than having the sun and the planets orbit the Earth. So that was very important, and of course it got Galileo in trouble eventually. Equally important, though, were these observations of a stellar Milky Way and that both the sun and the moon were not perfect. because that was one of the things that helped make the transition from this earlier universe in which the heavens were a perfect celestial place, completely separated from the Earth. This was the first kind of clue that not only were the heavens not permanent and unchanging, but they were very like what we have here on Earth. So that was another very important contribution that he made. I want to just make a mention of a really neat theme semester event which is about to begin here. The special collections of the library here at the University of Michigan has, for reasons I'm not entirely sure of, an incredible collection of historical texts in astronomy and mathematics. And because of the theme semester, they're about to put those on display. This display will begin on the 7th floor of the Hatcher Graduate Library. It will begin on Monday and will continue through April 11th. This display will include first editions, very first editions, of not only Galileo's Sidereus Nuncius, but also the principal works of Copernicus, Kepler, Tycho Brahe, and others. I mean, it's amazing that a few hundred yards from here, all these books exist. And it's wonderful that we all get the chance to go and see them. So I would definitely carve out some time in your schedule to go and see it. It's a very rare opportunity to have a personal contact with the history of science like this. All right, at the same time that Galileo was doing this work, a little bit farther north, his contemporary, Johannes Kepler, spent many years digesting observations of planetary motions that were recorded by his sometime employer, Tycho Brahe. And what Kepler found when he analyzed these things was a set of remarkable but really unexplained patterns. So this is the first place we'll talk about patterns like that. He found these really amazing patterns in the nature of the orbits of the planets. And he encoded them in 3 laws which he had no explanation for at all. The first one said that all the planets orbit the sun in ellipses rather than circles, and that the sun stands at one of the foci of these ellipses. Ellipses were geometric constructions that were well understood at the time. Not only that, the speed of these planets as they orbit around in this elliptical orbit, their speeds change with time, but in a very regular way. They change in such a way that a line drawn between the sun and that planet will sweep out an area in some period of time, which is the same all the time. The crucial fact about these patterns that Kepler observed is that they're not like a loose description of what's going on. They're incredibly precise, these patterns. If you want to show this one, for example, you can plot the cube of the size of the orbit against the square of the orbital period, and what you find is that all the planets in the solar system fall right on this line. It's not approximate, it's not, rough. It's really precise. And the precision of this pattern that Kepler observed was very important. It provides a real challenge. Any theory which attempts to explain planetary motion must include this, right? We'll see this come up over and over again. Patterns that are seen in nature that are real and robust. And they must be explained by any theory that wants to comprehend them. Fortunately for Kepler, it would only be a lifetime or so before Newton solved this problem. Newton is our first input of real theory into this. And what Newton did was to create a tidy system for understanding all the things that were seen in Kepler's laws. He made enormous and wide-ranging contributions to all kinds of science, but the most fundamental impact he had on astrophysics was a simple thing. What he did was to show us that the laws of physics that apply here on the Earth, the mundane laws of physics that apply down here in our world, are exactly the same laws that apply everywhere in the universe. They're universal laws. So the laws that we might get by studying things in the laboratory here are things that apply everywhere in the universe. In one step like this, he transformed the universe from cleanly divided into heaven and earth to something that was united. To do this, he had 2 tasks. First, he had the small task of explaining everything that happens on Earth. Right? So he wanted to explain all of mundane motion with mechanics. And he gave us the toolkit, which we still use to explain the motions of all ordinary things here on the Earth. Once he did that, he applied these new laws of motion that he had discovered to show that one law, the same universal law of gravity, could explain not only how an apple falls here on the Earth, but how planets orbit the sun. Newton's ability to do this, to predict the motion of planets with a few really simple laws, was truly shocking to his contemporaries. When they saw that a few simple laws could predict things that they thought were imposed on the universe by something much more complex, they could see that there were simple rules underlying it. They believed that what Newton had discovered was true with a capital T, right? Really the truth, not a rough approximation to it. So it's very important that Newton had this example where he could go out to the planetary motions and make very, very precise predictions of planetary motions. If he tried to predict, for example, the motion of a ball flying through the air, it would have been much, much less precise. And people would have been much, much less impressed than they were when they saw what he did with the planets. So astrophysics gave a great contribution to physics there by providing an example that was exceedingly precise. It enabled Newton to show the power of a reductionist worldview like that, something that was not so clear before. And there are many famous statements of this. Here's a portrait of Newton done by William Blake. Here's a quote from Alexander Pope. You know, nature and nature's laws lay hid by night. God said, let Newton be, and all was light. Right? Quite an important achievement. Not content with theory, however, Newton made a number of instrumental contributions to astrophysics. He invented the reflecting telescope, a telescope that uses a mirror as an objective instead of a lens. And he did this because the reflecting telescope eliminated a problem with lenses called chromatic aberration. But today, this advance is important primarily because it allows us to make enormous objectives that we support from behind instead of from the edge, the way we do with lenses. So that was an important contribution. He also invented the spectrograph, an instrument that's designed to take the light from something like the sun and disperse it into its colors to allow us to see what the constituents of some light are. Newton called this spread out light from a source the spectrum of that object. And this spectrograph allows us to learn more about the light from an object than we would otherwise be able to obtain just with our eyes. We can see the color of an object, but not nearly as precisely as you can with a spectrograph. Just as we can see the stars, but not as precisely as you can with a telescope. And we have just a little reminder here of how this works. We send some white light from this slide projector here, and you can see that it's white light if I put my hand in it. It's just nice white light. We send it through these three prisms here. The light is both bent in its path and also dispersed to spread out its colors, going from red to green to blue. There are three different little spectra here because we have three different little prisms in the stand here. That's the only reason. So the three prisms in the stand disperse it a little differently. So remember that Newton gave us that. He showed us that you could take the light of an object, spread it out, and understand it more. That was another important contribution that he made. All right. Now we're going to skip ahead. As I said, we're going to move along pretty rapidly. We're going to skip ahead into the 19th century. So Newton was doing this stuff at the end of the 17th century. We're going to go ahead to the 19th century. At this time, the production of glass and optics had become a big business. There were, in the early 19th century, many wars to be fought. And the market for quality optics, even then, was not driven by astronomy. It was driven by the military, right? And this guy, Joseph Fraunhofer, a brilliant German manufacturer of optics, was trying to eliminate the chromatic aberration in a little telescope that was so annoying. Right? He had customers who wanted telescopes that didn't have chromatic aberration. In doing this, he needed to study the way that glass bends different colors of light differently, what's called the dispersion of the glass. And so he was working on trying to understand the dispersion of glass as precisely as possible. And that very practical pursuit led him to construct the best spectrographs by far that had ever been made, much better than the spectrographs that Newton had been able to make. He used for his dispersing element both the prisms that we see there and also a new invention that he'd made, recognizing the wave nature of light, something called a dispersion grating. And the dispersion grating was important because it allowed him to quantify the measurement of the wavelengths of light, something that had been nearly impossible to do before. So just like Newton, he applied his new spectrographs to the spectrum of light from the sun. And in addition to seeing the rainbow of light that Newton saw, Fraunhofer saw something that really surprised him. He saw a complete forest of dark lines superimposed on the rainbow of light from the sun. Now, the reason that Newton didn't see this is because Newton sent in light that was very broad in aperture. I'll show you this in a little bit. Very broad in aperture so that the spectrum of each little part was washed out with its neighbors. So if you took this and just smeared it, you wouldn't see these lines, right? And so Newton didn't see these lines, but Fraunhofer did. An amazing pattern of hundreds, I think 576 that he cataloged, lines that he saw in the spectrum of the sun. Okay? This is another pattern, something remarkable, a feature of the light that he saw from the sun that begged explanation. It was a very precise thing. It was there every day. It was very much the same kind of thing. All right, so some kind of explanation was needed here. This explanation would actually take a while, and there was an intermediate step that's nice to talk about. The secrets of Fraunhofer's dark lines were partially resolved in laboratory experiments that were done in the 1850s by Gustav Kirchhoff and Robert Bunsen. And I think it's kind of funny. If you've ever studied science, you've probably heard the names of Kirchhoff and Bunsen before, but not necessarily in association with this, which is by far the most important thing they did. Other things are named for them, too. What these two continentals did was to understand some fundamental things about the interaction between light and matter, and they are summarized in 3 principles of spectroscopy that Kirchhoff first wrote down. The first one says that if you have a dense object like a solid and it's very hot, it will emit a continuous spectrum of light, the rainbow that Newton saw when he looked at the light from the sun. The second thing they realized is that if instead of a hot, dense object like a solid, you have a very hot gas, that gas will emit light that is almost completely different from that continuous spectrum. It will emit something where there are very specific wavelengths of light that are emitted brightly and nothing else. This is what's called an emission line spectrum. And here are a few examples of them. We're going to look at some in just a second as well. Different elements produce emission line spectra, which have different patterns. So they realized that if you saw the pattern, you would know what element was producing it. So these were emission line spectra that they saw emitted by hot gas. But that, of course, isn't what Fraunhofer was looking at. He was seeing dark lines, not bright lines. So what were they? So what Kirchhoff and Bunsen realized was that if you have a hot, dense object like a solid, and it's surrounded by a tenuous gas, then when the light from that hot, dense object passes through that atmosphere of tenuous gas, it will be absorbed in narrow lines. And the absorption will have exactly the same pattern you see in the emission line spectrum, except it will be dark lines instead of light lines. Obviously, these laboratory experiments gave crucial insight into Fraunhofer's spectrum of the sun. The sun emits that kind of continuous spectrum. It's a hot, dense object emitting a continuous spectrum. When that passes through the atmosphere of the sun, it has specific colors, narrow little lines, absorbed by the atoms in the gas that's in the atmosphere of the sun. So that's huge, of course. It enables people, for the first time, to have a chance to figure out what an astronomically distant object is made of. Just a few years before this, some of the world's leading scientists were arguing that figuring out what stars were made of was one of the things that was, in principle, impossible to do. Right? So it's a very important advance that was made when this spectroscopy was begun. I have a demonstration to show you that will show us some of these features. In fact, I think we'll be able to show all of the main features of Kirchhoff's 3 basic principles. So what I'm going to do is first I'm going to turn on a light here, which will allow us to look at the output of this spectrograph. And before I do that, I'm just going to go back quickly to the slides that I had. Let's see, we'll get that back up. Go back quickly to the slides that I have so I can show you what's going on in this spectrograph. Okay? This spectrograph is a device. This one is one very like what we see in this picture. It has a little place here where the light goes in, and there's a very narrow slit at that input. That narrow slit collimates the beam so that I don't have a spectrum from this spot overlapping a spectrum from that spot and that spot and that spot. Remember how we said Newton was washing this out by doing that? So if we narrow it down and look at just a narrow slit, we'll see features that we couldn't see otherwise. Okay, so that's the input, a little narrow slit for collimation. The light then comes to the middle of this spectrograph where it encounters a dispersing element. And in an old spectrograph, this might have been a prism. In this case, it's something called a diffraction grating, the kind of thing that Fraunhofer invented to do this. That disperses the light, spreading it out like we saw that prism do right here. That spread out light then goes into this little telescope here. It's really more of a microscope, which we would normally put our eye up to and look at the spectrum that comes out. But so that you can all see it, we've instead put a television camera on that. So we will see what comes out of the spectrograph show up on this television camera. So now I'll switch back to that so that you can see it. And what we will see is first the continuous spectrum that's produced by a bright object. And I should say there are some features on this that might confuse you, so I want to be clear about it. Do you see this line? That line is part of a crosshair in the little microscope. Not important, okay? The other thing that you will see is a bunch of horizontal bands. Those horizontal bands are produced by imperfections in the little slit that we have here. So they're like shadows, and they're also not important, okay? When we see something that is important, I'll try to point it out. There will be something. So the first thing is there's a continuous spectrum, a rainbow here, right? So I should be able to sweep this back and forth, and what we see is we come into red light, and then we go through green, and finally shift into blue, okay? So you can see that there is this spectrum. Interestingly, as you watch it fade out, it makes you wonder, doesn't it? Does it really stop there? And it doesn't. It's just you can't see it, and neither can I, all right? So there is, on this side of this spectrum, ultraviolet light that's going through, and on the other side, when we get to red and go beyond it, it's infrared light, okay? So both of those kinds of things are here. Now I'm going to try and position it in about the right place. See if I can do that. All right, so that is a continuous spectrum. The second thing Kirchhoff said should exist is if you have a really hot gas, it should produce an emission line spectrum, a spectrum that has nothing in it except these narrow lines. So what we have here is an oven that is heating up a bunch of mercury, okay? I'm sorry, it's sodium, not mercury. So we have a bunch of sodium in there, and it's been heated so hot that it's become a hot glowing gas. There's a really hot little oven here that's producing this. And what I need to do is to find the emission lines that it produces. So let's see if I can do that. Oh, there they are. Look at that. So you see these lines here? Let's look at it over here. See these two lines? Those lines are produced as emission lines from sodium. Okay? 2 lines, emission lines. As I sweep this thing around, we can look and see if there are other colors here. You know, and what we see is there's nothing else. Oh, there they are. Right? Those 2 emission lines. So that's the second thing that Kirchhoff said would happen. If you have a hot, tenuous gas, it will produce an emission line spectrum. But this is not what you see from the sun. What you see from the sun is an absorption line spectrum. And in order to do that, we have to have a continuous source, like this. And then we have to insert in front of it some tenuous gas, which contains that element. So how are we going to do that? We want sodium, because it's a sodium line. So what we have here is some salt water, and I'll show you that it is. I'll just drink a little. Very salty. And then we have a way of turning it into gas, which is what's the name of this burner? A Bunsen burner, right, Mr. Bunsen. Why did he invent it? To do this. They wanted a way of burning gas, right? So what you see now is you don't see any absorption lines due to this, because I haven't put any salt into the beam yet. To put salt into the beam, I'll take this thing, dip it in the salt water, and put it into the beam. And what you see is a dark absorption line appear. Okay, let's see if we can see that up here. See that dark line that's coming and going? The vertical line? That's the absorption line of sodium. I have to be careful here. I don't want to stick my arm in that. All right? See that dark absorption line appearing? That is the absorption line that Fraunhofer saw in the spectrum of the sun. That's the same kind of thing that he was seeing in the spectrum of the sun. Okay? So with this apparatus, we can demonstrate through the same instrument the continuous spectrum emitted by a hot object, the emission spectrum emitted by a hot tenuous gas, and finally the absorption line spectrum that is observed when you send a continuous spectrum through a hot gas like that. One more thing I want to mention about this. These detailed spectra let you not only learn about the composition of an object, which is obviously very important, they also let you learn something about how the object is moving. Now, there's this famous Doppler effect that you're probably all familiar with, that if a sound is moving toward and away from you, you will hear it differently. So this demonstration is kind of annoying, so we won't do it for too long. First, it makes this sound. If I spin this around my head, you will hear the sound change as it comes toward you and away from you. That's the Doppler effect, okay? It's the same effect that you hear if there is an ambulance that drives toward you and then passes you, the frequency changes. Well, Fizeau in 1848 realized that the same thing would happen with light, and that if a star was moving toward or away from us, those absorption spectra lines that Fraunhofer seen would be shifted one way or the other, and you'd be able to measure how that star is moving. Little did he know how important this would be in the future of astrophysics, because now that we realize the universe is so dynamic that things are really changing, we see things that are moving relative to us, not just a little, but an enormous amount. This is just something to illustrate that. These are quasar spectra from the Sloan Digital Sky Survey. And what you're looking at here is an emission line shown in the spectra of about 60,000 quasars, ordered by how fast they're moving away from us. So you see this line shift more and more and more toward the red as they move away from us faster and faster and faster. So this turns out to be a really important, crucial element of astrophysics in the future that also comes from spectroscopy. So spectroscopy is really very crucial in astrophysics, especially in connecting the physics of the world to what we see in the sky. Okay, our next step is an extraordinary digest. All right? During the 19th and 20th century, physics back here in the labs on the Earth was doing a wide range of amazing things. Earthbound physicists during this period finally developed a really thorough predictive theory for the interaction between light and matter. It provides an explanation of both the emission and absorption of light. It involves many aspects of physics, the great achievements of the 19th and early 20th century: thermodynamics, electricity and magnetism, statistical physics, quantum mechanics at the beginning of the 20th century. All of these things were needed to give us the main pieces that we have to understand the light emitted from an object or absorbed by matter. They allow us, having these tools, allows us to predict what sort of light an object ought to emit. And that's very useful if you're looking at the light from an object and you want to interpret it. Because you can make predictions. You can say, well, maybe it's this. What would that look like? Maybe it's that. What would that look like? And that toolkit is what enables us to interpret some of the really bizarre things that we see being emitted by objects out in the universe. Okay? Really crucial thing. This knowledge allows the interpretation of those distant objects. Almost as soon as the main features of quantum mechanics were in place, a brilliant young astronomer put them to use to discover nothing less than what the universe is made of. Cecilia Payne-Gaposchkin, someone who should be much more famous than she is, had studied physics and chemistry at Cambridge, but they never gave her a degree because they never gave any degrees to women at the time. After this, she moved to Harvard, and she completed there what has been described as undoubtedly the most brilliant PhD thesis ever written in astronomy. Okay? I have a copy of it right here. It's quite a special thing. What did she do? It had been known for a long time that the absorption spectra of stars, not just the sun, but all the other stars, people were now measuring the absorption spectra, the kind of Fraunhofer spectra of all those stars, that they were very different one from the other. And astronomers had placed these, looking at this pattern, they had placed these into different classes. They argued vociferously about which of these different classes was correct. Now, arguing about this, like when you see arguing like this going on in science, then you know that nobody has the evidence. Because if you don't have the evidence, all you can do is yell. Right? And if you have the evidence, you don't have to yell. Right? You just show the evidence. So when you see scientists arguing bitterly about something, you know you should just wait, because eventually it'll get sorted out. All right? They put stars into different classes. Eventually, by 1922, there was a pretty well-established system called the Harvard system, which ranks stars according to different classes that run through O, B, A, F, G, K, and M stars. All right? Again, there was no real understanding of these classes. It seemed they formed a continuous sequence, but there wasn't any physical understanding of what they were. This O, B, F, G, K, M sequence, of course, is famous among students of astronomy since 1922, and there are all kinds of mnemonics for remembering that sequence, which one comes first. The most famous one from the very early days, "Oh, be a fine girl, kiss me." And the more modern one, there's actually whole web pages of these, right? Because it's a fun kind of exercise. But I found one recently that I like. "Only boys accepting feminism get kissed meaningfully." So, and I leave it to you to think up your own, but I like that one. Okay. So these classifications seem significant, but no one knew where they were coming from, what they meant. Most people thought that these different classifications had to do with chemical composition. After all, you're seeing a bunch of different lines, must be different, that stars are made of different stuff. Okay? what Cecilia Payne-Gaposchkin did was apply the latest ideas of quantum mechanics and statistical physics to understand that, in fact, these different stellar classes don't reflect chemical composition, but just different temperatures in the stars. Okay? So that is a sequence of temperature, not a sequence of chemical composition or anything else. It's really temperature that's the governing parameter. Just to give you an example of this, here's that same spectrum now showing what are the temperatures of these stars. A one-parameter kind of a sequence. Now, if it's a one-parameter sequence, that means the stars must all be pretty much the same in other ways, and the way in which they're pretty much the same was an enormous surprise. These stars are, all of them, made almost entirely of hydrogen and helium. All right? This was something that came inevitably out of the calculations that she did very robustly in her results. But it was shocking because, after all, the Earth is not made mostly of hydrogen and helium. We had a good census of what the mix of elements on the Earth was, and so people were very surprised to see this. Her thesis advisor, a great astronomer named Henry Norris Russell, was so skeptical of this result that he asked her to put in her thesis a statement about it. So here's the statement that he got her to put in the thesis. Although hydrogen and helium are manifestly very abundant in stellar atmospheres. That's Cecilia saying, you know, the data doesn't lie. The actual values derived from estimates of marginal appearance are regarded as spurious. So I can see the result, I know it's there, but I'm not allowed to really say so. So we'll take it out. It's okay, it turned out that she was clearly right, and a few years later, everyone acknowledged it. What does this mean? I mean, the universe is mostly made of light elements. It's dominated by light elements, like more than 99% of it. So everything that we're made of, except that little bit of hydrogen that's in you, everything that we're made of is just kind of the frosting. It's a little bit of extra stuff that happens to exist in the universe. What really counts is the hydrogen and helium. Quite a shocking discovery, quite an important one. Okay, let's jump back to instruments, because a huge number of things are happening with instruments in the 19th century. Perhaps the most important one has to do with photography. Telescopes had allowed our eyes to see things that were otherwise invisible to us, and spectrograph had allowed our eyes to analyze light in a way that was not possible before. To go to the next really big advance, we had to do something beyond letting our eyes be a major element in the system. We had to construct entirely new eyes that are able to gather up light for hours at a time. And not only that, eyes that are physically enormous. We needed both of these things to make the next big advance. The first advance was made by the application of photography to astronomy, which started quite early in the 1840s, even very early in the history of photography, but really took off in the 1880s when people like Henry Draper figured out how to get the right exposure doing astrophotography. Very quickly, these early astrophotographs revealed details of the universe that were invisible to even the sharpest eyes. So this fact, the fact that they were seeing new things, made scientists suddenly furiously hungry for more light. Right? They really wanted to get more light. And the way to get more light was not just to gather up light for hours like this on photographic plates. To hit the jackpot, we needed bigger eyes. And no one felt this need for bigger eyes more than this man, George Ellery Hale. He wanted big telescopes that you could put photographic plates on like this. Okay? Hale was a man of his time, and he had no small plans. He started out in Chicago, where he constructed the largest refracting telescope ever built, then or since, the Yerkes 40-inch. This is a picture of it in recent days. It's quite an amazing instrument. You can see it's very long. It occupies an enormous dome. In fact, this dome is much bigger than the dome that the world's largest telescope is in now, because the world's largest telescope is so much more compact than the Yerkes telescope. So he did that. He completed that in 1895. This is in southern Wisconsin at the Yerkes Observatory. If you're ever in that region, it's a wonderful place to visit. This was the end of the line for refractors, though, mostly because in a refracting telescope, you have a lens, something like this one. Right, this is a really big lens. And this lens, you can't support it by putting anything in the middle, right, or it would block the light. You have to support it at the edge, the way we've done here. And that's okay if the lens is going to stand upright like this, but for those of you who have any kind of mechanical engineering in your mind, if you take this lens and you turn it in different directions, as you must on a telescope, it's going to sag, right? It's very hard to support it and have it maintain the shape that it needs to in order to focus light correctly. This should give you some sense, actually, of how big the Yerkes refractor is. This lens is 48 inches across, And the Yerkes refractor is 40 inches across. So this is actually a little bit bigger. But of course, it's not in a telescope, is it? Right? It's not going to be either. All right, so Hale built a 40-inch. Then he shifted to reflecting telescopes for this reason. You can support the mirror from behind, no problem. Make it almost as big as you want. He went to California as well, because Wisconsin's actually, believe it or not the best observing site in the world. The reasons that he built it there were purely financial. The man Yerkes, who funded the telescope, insisted on two things. It should be within 100 miles of Chicago, so that he could take his rich friends there. And second, it needed to be the biggest telescope in the world. And that's all he cared. As long as that was met, he would be happy. So Hale moved to California, where he founded the Mount Wilson Observatory in 1904. The site chosen for this observatory was in the dark hills above a sleepy little hamlet called Los Angeles. All right, so it was a great place to put an observatory in 1904, but that didn't last very long. At Mount Wilson, Hale built several new record-breaking telescopes, including the 60-inch, which was commissioned in 1908, so already quite a bit bigger than the 40-inch. And in 1917, a very famous, very important telescope called the Hooker Telescope, or more famously in astronomy, just the 100-inch. Right? Crossing 100 inches was obviously an important achievement. These giant telescopes, especially the 100-inch, opened up for the first time the possibility of serious extragalactic astronomy. And we'll talk about that in just a second. Hale wasn't through with the 100-inch or with Mount Wilson. He was an amazingly ambitious person, as I've said. He helped to found Caltech. And he also went on to build a new observatory in a slightly quieter part of San Diego County, a place called Mount Palomar, where he built the 200-inch telescope. Or I should say he started building the 200-inch telescope. This telescope was begun in 1928. Hale died in 1938. And the telescope turned on in 1948. All right? So it was really more than a lifetime kind of endeavor. This telescope, a 200-inch telescope, a 5-meter telescope, is still one of the most powerful instruments in the world. Still a very, very important and powerful telescope. And fortunately, it is called, as it should be, the Hale Telescope, something he certainly deserves. Okay, now the pace has to pick up. We have only 10 minutes left. And events begin to overlap and blur. Photographs in large telescopes created the first data tsunami in astronomy. Right? All of a sudden, not only could you go tonight and look and draw a picture maybe, there were all these photographs being taken all over the world. Tons of data coming in. And this, of course, was at a time when there are no electronic computers and no digital detectors. So digesting and summarizing this data required really careful, dedicated people. One particularly remarkable team in this group was a group called the Harvard Calculators. And when people use the word calculator, they use it in the same sense that we do now for the electronic calculator. Calculators were hired not only to do astronomy, but to do calculations in different kinds of engineering, for example, where you just had pages and pages of algebra that you had to work through. These calculators were a group of women astronomers, including such remarkable figures as Annie Jump Cannon and Henrietta Leavitt. What Leavitt did, these women did a number of really remarkable things, but what Leavitt did was crucial for cosmology because she gave us a way to measure distances in astronomy. She discovered that there was a class of stars whose variations told us how far away they were. She came up with a way of looking at how a star varies to see how far away it really is. And that one step gave us the tool that we needed to measure the cosmos. She did that by looking at thousands and thousands of these photographic plates and digesting them in her mind, coming to an understanding of what they were. Other people then took this and ran with it. In particular, Edwin Hubble and Milton Humason used the Hooker 100-inch. And here's a picture of Hubble in the cage, in the prime focus cage at the Hooker 100-inch. There's the mirror down there. It comes up here to form an image, right? The objective forms an image, and you put a photographic plate in here and take a picture. And then you pull it out and you put another one in, and you sit up there all night long in the cold. All right? So they used the 100-inch to detect these variable stars that Henrietta Leavitt had discovered in nearby galaxies. So all of a sudden they had some stars in that nearby galaxy, and they could measure how far away it was. They measured the distances to nearby galaxies. Another heroic kind of astronomer, a guy named Vesto Slipher, was busy then measuring the spectra of galaxies, first to learn what they were made of, what was their chemical composition, and second, to measure their velocities. When these two things were put together, distances to galaxies and velocities of galaxies, by Edwin Hubble, what he found was a remarkable relationship. He found that all galaxies are moving away from us, almost all of them, and the farther away they are, the faster away they're moving. All right? This is another pattern observed in nature, like Keplers Laws or Fraunhofer's lines. And at first it was really not clearly understood. Later, Hubble would claim that he clearly understood it in the beginning, but it's clear from reading the papers that he really didn't. It was an interesting pattern, but it was not clearly understood. Ironically, there was a piece of theory already lying around for this. Einstein in 1917 had come up with a new conception of gravity, something called general relativity, that includes in it a framework for cosmic expansion. General relativity reimagines gravity as a consequence of space-time curvature rather than being a force in the usual sense. And so the way this works is that the matter that's in the universe tells the space-time how to curve, and then the space-time tells the matter how to move. The most surprising thing about this theory, maybe a little unnerving thing about this theory, is that it most naturally talks about universes that are not static, that are dynamic. It doesn't, the equations of general relativity, this is sort of an example of that. The equations of general relativity don't really tell you how the universe ought to change with time, but they tell you that it will change. It could be either expanding or contracting, but it's really hard to make the universe static in this kind of theory. So within this framework, though, that already existed, there was an explanation for Hubble's pattern that he observed, this fact that things farther away are moving away from us faster and faster. It was the expansion of the universe. Right? It was already there in this picture. And running that expansion backwards in time allowed people to predict that there should have been a hot, dense, early period in the universe. Okay? Lost in the first 350 years of astrophysical discovery was most of the information that every object in the universe sends to us. For almost all of history, we have viewed the universe through a kind of metaphorically narrow window. We have, instead of looking at the full spectrum of electromagnetic radiation that objects emit, a spectrum that ranges from meter-long radio waves to proton-sized gamma rays. Instead of that, we had looked at just this narrow window for optical astronomy. The reason for this is clear. Astronomers had not taken advantage of all this stuff because they couldn't see it. I mean, first of all, they couldn't see it with their eyes, but even once radio waves were understood, they weren't looking at it and didn't realize that they could do it. So it's really only in the last 50 to 70 years that this full spectrum of light has been made available to astronomers. It was made available not because humanity decided that it was so important for astronomy that we should go into space and put telescopes there. Of course, it was Cold War politics that helped on this one. Right? When Sputnik went up, all of a sudden, it was crucial to everyone to get into space. And fortunately, those people who went into space carried along with them telescopes for infrared and ultraviolet and X-ray and gamma ray light. I have one little demonstration just to show you one example of this. I have here a microwave transmitter, which emits microwave radiation. It's kind of radio radiation, and then a microwave receiver here. And we'll turn on the receiver so that it can receive the microwaves, and it will make a sound when it does. We can focus and bend microwave light in the same way that we focus and bend visible light. Instead of using glass optics, we can use a piece of paraffin wax. So this is a prism, like these prisms, but not a prism for visible light. It's a prism for microwaves. Remember how that prism bent the light? It was going that way and it went over here? We're going to bend the microwaves now. Okay? So I send the microwaves into the prism over here, and let's see where they come out. They come out bent over here. All right? If I take the prism away, it stops. I put the prism back, it gets picked up. It would get picked up better if I had this just at the right height. Okay? So this is an example of some of that invisible light that was then later used for astronomy. So this multi-wavelength astronomy that became possible is really like a grand extension of spectroscopy. What it does, just like spectroscopy did, is it lets us increase the breadth and precision of how we can interpret what we see out in the universe. I just showed two multi-wavelength sets of images here to give you some sense. One is the familiar sun, which when you look at it in visible light, well, it has sunspots like Galileo saw, but otherwise it's just a nice disk. If you look at it in X-rays or extreme ultraviolet, or two narrow bands within the optical, or infrared light or radio light, it looks different. And these pictures were all taken at the same time. So this structure that you see down here, these sunspots, you see it reflected in the X-rays all the way down into the radio. So you can get a sense of how a multi-wavelength image gives us a tremendous amount of information that we didn't have before. The other one is an example of a galaxy imaged in multi-wavelength. So you see that galaxy in X-rays and in optical and near-infrared and mid-infrared and far-infrared and radio. So you get the sense that we can measure the spectrum now across the whole spectrum instead of just in the narrow little realm of visible light. This race for technology that was going on, where astronomy was kind of just grabbing what was happening, brought two other enormous advances whose impact is still expanding through astrophysics. The first of these two was digital light detectors. Digital light detectors, the charge-coupled devices that power your cell phone cameras, among other things. Those digital light detectors are incredibly effective. They revolutionized optical astronomy. Not only did they allow data to be directly collected digitally and put into computers, which is very helpful, the most important thing they did was they are 40 to 80 times more sensitive than film. So it used to be Hale built this enormous telescope, gathered up all this light from a distant object, focused it onto the film, and 95% of it disappeared. Wasn't recorded. When you put one of these digital detectors on that, almost 100% of the light is collected. So putting a digital sensor like this on your telescope is just like making your telescope 50 times bigger than it was before. And that's had a huge impact. For professional astronomers, it's meant a race toward the most distant things. All of a sudden, telescopes are much more powerful, able to reach more distant things. For amateur astronomers, it's meant that most of what used to be professional astronomy is wide open. Right? You can buy one of these CCD cameras and put it on a telescope for not very much. And so a lot of people are doing things that could only have been done at the 100-inch 80 years ago. It's really a great big advance. Very important. The second big advance should be obvious. It's computers. Right? Computers are incredibly important. Their impact is everywhere in modern astrophysics, as it is in every part of modern science. Gathering data, analyzing it precisely, transmitting that data around the world, giving it away to other people so that they can use it in an easy way, and also making really precise predictions of complicated phenomena. Remember I said we know how light is emitted by objects, so we can make predictions for what they should look like. Those are really complicated, though. And if you have computers to help you make those predictions, you can do that much better. This is just my favorite supercomputer. It's run by some of my colleagues in Barcelona. It's actually inside a medieval church. So it's a pretty cool setting. Pretty cool setting. Now, computers have their drawbacks. For example, when my daughter Isabel was in preschool, someone asked her what her father did for a living, and she's a very precise, accurate young woman. She told them he types. And that's still the case, I'm afraid. All right. Here's the 20th century in one slide. The list of 20th century accomplishments in astrophysics is immense. But since it will be the subject of most of the remaining talks in this lecture series, I don't have to say much about it. I just want to say that the main thing I think that we did in the 20th century, the first most important thing, was to establish the basic origin of almost everything. We now know that the universe began in a hot, dense, expanding state, and that the light elements that Cecilia Payne-Gaposchkin found were cooked up in that early period. Since that time, it has continued to expand, while gravity forms planets and stars, where all of the heavier elements, including those that are in U, were cooked up, and galaxies and things like that. Okay? Working out the origin of everything is a significant achievement, and we should be very pleased with what the 20th century did for astrophysics. People have wanted to know this forever, and now we know. We don't know every detail, but we certainly know the basic story. It's a settled business. Okay? But we're not done. For one thing, we're missing some major pieces. There are some things here that are like the patterns that people had seen before, things we don't really understand. The universe we've found is dressed with ordinary matter, hydrogen, helium, stuff like what we're made out of. But it's mostly constructed of two things that are kind of the elephants in the room: dark matter and dark energy. This dark matter, this stuff that's out there, we can tell it's there with absolute certainty. It's there just as clearly as Fraunhofer's dark lines were. Right? You know, it's just not going away. It's there. Dark energy is a name for another kind of pattern like this, a surprising kind of acceleration in the expansion of the universe. In a way, these two modern mysteries are analogs of the old ones. They're like Fraunhofer's dark lines. And many of those old problems, remember, took lifetimes to sort out. So I think when we think about dark matter and dark energy, we shouldn't feel like, oh no, the whole house of cards is about to collapse. I don't think that's the case at all. And we shouldn't be surprised that 70 years after the first indications of dark matter, we still don't know the answer. These things take time. And we have a long history of success in applying that time. And after all, we need to leave something for the next 400 years to do, right? So I'm going to finish up just talking about the future. The future, as is famously said, is harder to predict than the past. But some things are clear. And so let me mention just a few. The first thing is that we are going to have more of everything that we have, right? But interestingly, we're not going to have incomprehensibly more than we have. Over the last decade, we have actually mapped out the distribution of galaxies over a significant fraction of the visible universe. And over the next 50 years, we're going to finish that. There won't be any part of the universe that we haven't pretty basically looked at. We'll have a map of what the whole universe is. All right? Don't despair, though. This is not really such bad news. After all, we've known everything in the solar system, sort of, for 200 years, and we still keep finding really amazing things right in our own backyard. So it's not like it's going to be over, but this is a great era, and one which we all should enjoy. The fact that we are the ones who get to map out the universe for the first time, just as the great explorers were the first ones who got to map out the Earth for the first time. It's a great time to be paying attention to this. The second thing is that our data will become much better. They will be more precise. They will be deeper, they will be more comprehensive than they have ever been before. And I'm happy to say that, at least at this point, it looks like computers will continue to advance faster than astronomers do for at least a while, so that we'll be able to deal with this data when it comes in. When I first started working on the Sloan Digital Sky Survey, we were panicked about the data that we were going to produce. How could we possibly analyze it? What we didn't realize is that most of the world was out there making a fortune producing bigger disk drives and faster computers so that you can watch movies online. Right? So as long as that continues to happen, as long as you want bandwidth and data and everything else, we'll be fine. Okay? The last thing on here is that we will get a few new things. And one example is gravity waves. Detecting gravity waves, which we're pretty darn sure are there, is very, very hard. But it's going to happen. And when it does, we will get one new view on the universe, something that we really haven't had before, something really different. For me, though, the most important thing in the future comes back to this theme of connecting what we have here in the mundane world and what's out there in the heavens. This possibility really got started about 15 years ago. Until 1995, every scientist thought there must be lots of planets around other stars. There have to be lots of planets around other stars. We understand the physics that's involved in that, but we didn't have the technology to prove it. In 1995, for the first time, we got the kind of technology we needed to prove it, and now hundreds of planets have been discovered, and thousands more are coming in just the next few years. So as soon as we were able to see this thing that we thought must be there, we did. Today, I think that almost every scientist believes that life must be widespread, but we don't have the technology to prove it yet. So the great triumph in astrophysics has been a unification of the heavens and the earth. Everything that's here is out there. And the very same laws of nature that drive the ferocious appetite of a supermassive black hole also rule how we drive our car down the road. Everything is connected in this way. So the next few generations of scientists have to take this final step. Life is here on Earth. We know how it works. It's a physical process, very complicated, fascinating. There's no reason it shouldn't be everywhere in the universe. And I'll go even farther. If we cannot find it, if we build the technology that should find it and we can't, something is really wrong with our scientific understanding of the universe. It's a real challenge. It's a real important challenge. It's impossible that life should be just here. So we can't prove it yet, but that's what I expect the next couple generations of scientists to do. I want you all to go out and get started on that now. 400 years of success is great, but we really have a lot more to do, and this is the most important question. So I hope what we'll see coming in a talk like this in a few hundred years is the life that's everywhere in the universe, too. Thank you very much.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. Remlois Tiffany Endowment, and by gifts from friends of the program.